The biggest shift here is that AI systems are getting better at adapting themselves without expensive retraining, without bloating prompts, and without brittle manual data curation. One line of work turns a repository's history into a compact adapter that stays current as code evolves. Another scales code RL by recombining atomic problem structure instead of handwriting more tasks. A third learns the hidden shape of a domain from examples and uses that to synthesize better training data. The common thread is simple: less manual supervision, more capability per token. Here's what that means in practice. Let's explore the first paper. Code 2 LoRa Hyper-Network Generated Adapters for Code Language Models under Software Evolution. Code 2 LoRa from the University of Waterloo reframes repository-level code adaptation as hypernetwork-generated LoRa rather than retrieval or per-repository fine-tuning using a frozen Qwen2 5 coder 1 5 B backbone and a frozen Qwen3 embedding 0 6 B repository encoder to emit adapters with 0 inference time token overhead. The paper introduces 2 modes: Code 2 LoRa, static maps, 1 repository snapshot to adapters for stable codebases, while Code 2 LoRa, Evo, adds a GRU over sequential code diffs to refresh the adapter as software evolves. To evaluate this idea, the authors build Repo Peft Bench, a benchmark of 604 Python repositories with 39,612 static training tasks, 215,129 evolution track training tasks, and a 9-2 repository temporal holdout. On the static track, Code 2 LoRa, static reaches 63.8% cross-repo exact match and 66.2% in-repo exact match, beating the strongest baseline by 9.9 percentage points and matching the per-repository LoRa upper bound. On the evolution track, Code 2 LoRa, Evo reaches 60.3% cross-repo exact match and 64.5% in-repo exact match, improving by 5.2 points over a single shared LoRa and outperforming static snapshot adaptation under commit level drift. The paper also reports that Code 2 LoRa, Evo remains strongest on the 9-2 repository out-of-distribution holdout at 74.1% exact match, while preserving the key deployment advantage of no extra inference tokens. Let's explore the second paper, Combinatorial Synthesis Scaling Code RLVR via Atomic Decomposition and Recombination. This paper, from the Chinese Academy of Sciences and collaborating universities, introduces atomic decomposition and recombination, ADR, a fully automated framework for scaling code reinforcement learning with verifiable rewards by generating tasks from atomic, logical elements rather than heuristic seed expansion. ADR first extracts a compact element schema from C problems, then uses controlled recombination, template-based synthesis, execution-grounded validation, and adversarial solution space refinement to produce novel, solvable, and harder verifiable code tasks. The paper formalizes a 4-dimensional quality taxonomy: originality, difficulty, diversity, and test quality, and reports that ADR reaches 28.91 originality, 71.89 difficulty, 84.36 diversity, and 81.36 test quality, versus Educational Instructs 6.04 originality. On LiveCode Bench v5 and v6, ADR trained on Qwen2 5, Coder 7, B, Instruct achieves 25.37% and 26.14%. Pass at 1, outperforming Codcode's 22.75% and 23.57%, and the same approach lifts Qwen 3, 8B to 35.85% and 31.43%. In training dynamics, ADR delivers a plus 4.79% pass at 8 gain, compared with only plus 0.6% for the strongest baseline, showing that the method expands the model's capability frontier rather than merely increasing sample density. The framework also transfers to tool usage and data science, reaching 41.67% on BigCode Bench and 42.44% on DS1000. Let's explore the third paper, Domain-Specific Data Synthesis for LLMs via Minimal Sufficient Representation Learning. Domino, from Vivo AI Lab, Ant Group, and Zhejiang University, tackles domain-specific data synthesis when the target domain is only given by reference examples rather than a natural language specification. The method learns a minimal sufficient domain representation with soft prompt tuning, then adds a contrastive disentanglement objective that separates shared domain structure from sample-specific noise, so the learned prompt generalizes instead of memorizing. On LiveCodeBench's implicit coding domains, Domino is trained on 713 live code generation references and 66 live code execution references, synthesizes 80K and 40K samples respectively, and fine-tuning on its synthetic data lifts. Pass at 1 by up to 4.63% over strong instruction-tuned backbones. In the main coding results, Domino reaches 12.63 pass at 1 on live code generation and 42.59 pass at 1 on live code execution with OpenCoder, 8B, Instruct, and 17.31 and 56.48 with Quinn 2. 5. Coder, 7B, Instruct, while also surpassing the instruction-tuned backbone on LiveBench-style instruction following with a 55.39 average score. The paper's theoretical claim is that disentanglement expands the effective support of the synthetic distribution, and the empirical analyses support that with broader TSNE spread, stronger robustness across temperatures from 0.2 to 1, and better performance as domain soft token capacity increases from 64 to 512. Overall, Domino reframes synthetic data generation as inductive representation learning for domains that are hard to describe explicitly, with Ant Group's and Vivo AI Labs implementation showing that self-generated, domain-aligned data can outperform manual prompt design. That's a wrap on today's AI paper highlights. Thanks for watching.